Okay, so let us continue our solutions next with this one. We have to find all positive integers n such that the order of the group un equals 24. We already know what un is. Un is the group of integers modulo n that are relatively prime to n under multiplication modulo n. And we also already know what this order is, that is what its formula is. It is the Euler phi function value of the positive integer n. So that means we are required to find those positive integers n for which phi of n, which is nothing but the order of this group, is equal to 24. Okay. Since phi of 1 by definition is 1, we must have n greater than 1, because n cannot be 1. If n is 1, then this must be 1. It is not 24. So that means n is a positive integer greater than 1. So by the prime factorization theorem or the fundamental theorem of arithmetic, whatever you may want to call it, so by the fundamental theorem of arithmetic, there exist distinct primes, say p1, p2, etc., pn, and positive integers k1, k2, and so on, km, such that n has this prime factorization. Okay. Thus, we are seeking those n for which phi of n. Now if n has this prime factorization, we already know what phi of n is, or I mean what it ultimately turns out to be. It is this p1 to the power k1 minus 1, p2 to the power k2 minus 1, like that, pm to the power km minus 1 times P1 minus 1 times P2 minus 1, etc. Pm minus 1. That's what phi of n is if this is the prime factorization of n. And this is equal to phi of n is equal to 24. Let us also write the prime factorization for 24. This is 2 cube times 3. Now somehow from this equation itself we have to find all the possible values of n. So how can we do that? For that we have to use number theoretic arguments. Like for example, you see that the right hand side has only 1 3. So on this left hand side also we should have only a single 3, and that's just it. Note one more thing, that the number of primes involved in the prime factorization of n, that is also something we don't know, so we have kept that thing also some positive integer m which we actually don't know. Okay, so we now start off our number theoretic arguments with this 3. Since three divides 24, we must have 3 dividing this one also. There is no need to write this second term, I mean it's understood, it's there. Like that here also there is no need to write P2 minus 1. Okay, now because 3 is the prime, that means 3 has to divide at least one of these factors. Now there you can clearly see there are two types of factors here. Some factors are powers of primes, but some are prime minus 1. They look like that. So we actually have two different cases. Let 3 divide pi minus 1. Let us consider this case first. For some I lying between I varying from 1 to n. Okay. The only primes. Okay, now by the way, what does this mean? It means that pi minus 1 is a multiple of 3. That means it looks like this for some integer k. That means pi should look like this. Pi should itself be of the form 3k plus 1 then. So we are now going to look at those primes pi which are of this form 3k plus 1 and at the same time which are less than or equal to 24, because this entire thing, this product, is the left hand side and that we have assumed to be equal to 24. That should be 24, that is our condition. So each individual factor should be less than or equal to 24. So let us first apply that condition and let's see where that leads us. The only primes, or okay, perhaps I should write, before writing this sentence I should write this. Thus Pi is equal to 3k plus 1 for some positive integer k. Positive and not non-negative, because k equal to 0 is not an option. If k is 0, pi is 1, which is of course not possible for any prime pi. So positive integer k. Now the only primes pi of the form three k plus 1 such that this extra condition of course should also be taken into account, that pi is less than or equal to 24 r. You just start putting positive integers in place of k and see what you get. K equal to 0 of course is not an option, k is a positive integer. So let us start by taking k equal to 1. 3 plus 1 is 4, that is not a prime. K equal to 2. 3 times 2 plus 1 is 7, that is a prime. 3 times 3 plus 1 is 10, no. 3 times 4 plus 1 is 13, that is again a prime. 3 times 5 plus 1 is 16, that's not an option. 3 times 6 plus 1 is 19, that is an option. Can we take higher values of k? Because we have already reached 19. So 19 we are getting by putting k equal to 6. 3 times 7 plus 1 is 22, not a prime. 3 times 8 plus 1 is 25, not a prime. 3 times 9 plus 1 is 28, not a prime. 3 times 10 plus 1 is 31, that is a prime, but we have already exceeded 24. So these are the only possibilities. Okay. Now if pi is equal to 19, then uh, 18 divides this number, because pi minus 1 appears here somewhere among these factors. So we can directly write 18 divides, or we can actually show also what 18 actually is in this context. 18, which is pi minus 1, divides this thing, which we are not again writing, but in its place we write phi of n, because this is what phi of n is, and that is equal to 24. And that is not possible, of course. Why? Because 9 divides 18, but 9 does not divide 24. You can view it that way also. There, in the prime factorization of 18, there are two threes, 3 square is there. However, in the prime factorization of 24, there is only 1 3. A contradiction. Or we can just simply write like this, which is not possible. So Pi cannot be negative. That means we are left with only those two possibilities, 7 and 13. Now we are going to take each one of them separately. Let Pi be equal to 7. Okay. Now if you just like this one, consider Pi minus 1 again for Pi equal to 7, you get 6, and 6 does divide 24, so there is no problem with this one. But there is something else. That is not a problem, that's just an observation that will help us decide what the exponent of that prime Pi should be. If the exponent of the prime Pi is of course Ki according to our notation. So if Ki is greater than or equal to 2. Okay, am I wait, just let me see one thing. Oh, we don't have to. Okay, now only I am seeing this. So we cannot exactly go like this, the argument that I have here. So what can I do instead? There is actually no need to consider Ki. In fact, considering Ki will make matters more complicated. Instead, we can just simply think of n as a whole. If n, if 7 square divides n, if 7 square is dividing n, but that is precisely what I was going to write now. Anyway, let's just see what I'm trying to say here. If 7 square divides n, then seven should divide 24. Does it make sense? It is because you see 7 square dividing n actually is just equivalent to having this. So that means our Pi to the power Ki, that is there in the prime factorization of n, that is equal to 7 to the power Ki, where we can write 7 to the power Ki as times 7 square. Now when we calculate the phi value of n, actually what we are doing, we are calculating the phi value of each separate prime power separately and then taking their product, because the Euler phi function is multiplicative. Now among these factors there is one which is this 7 to the power ki. So we don't have to look at the entire thing, we just concentrate on this. This equals 7 to the power ki minus 1 times 7 minus 1 according to the formula for the phi value of the prime power. Now 7 minus 1 is 6, and that 6 in fact is the 6 which divides 24, so that thing is here. But simultaneously we have this factor also which appears here in this region of the product. Now because ki is greater than or equal to 2, ki minus 1 is greater than or equal to 1. That means in this power actually there is a 7, at least one 7. There may be more 7s. This may actually turn out to be 7 square also if ki is in fact 3. But the point here is that if ki is greater than or equal to 2, then this being a part of this product should divide 24. Why? Because this thing in fact is equal to 24, the entire thing. And this is not possible, of course, because 7 does not divide 24. Okay, so that means, okay, so why did I think that I was going to mess things up by considering ki? I got confused. We can in fact start with this itself, because now this is looking more confusing. So let me just write the argument, and then things, you will see that things fell in place, and this will in fact give us a clue about what is going on. If ki is greater than or equal to 2, then phi of 7 to the power ki, which is equal to this, we are exactly showing what the formula is. This should divide 24, and so 7 should divide 24, and that thing is coming from here, that 7 is coming from here, which we are not writing the reason explicitly, that because ki minus 1 is at least 1, that's why this is happening. That is understandable from here. Since this is not possible, we must have ki equal to 1. Ki cannot be equal to 0, because all the ki's, if you go back to our thing where we wrote about these pi's and ki's, all the ki's have been considered to be positive integer exponents. So that means the only possibility is ki being 1. Thus, or then, n is of this form 7k. I hope I did not use k anywhere else. Here I have used k, but that is not a permanent thing. It's just telling us the form that pi should take. Okay, this k, or if you find it confusing, we can just use another letter. No, we do not lack letters. Let us use L, the next one. 7L, where this condition is important, because we are considering ki to be equal to 1. So the largest power of 7, that is dividing our actual integer n, is 7 itself, that is 7 to the power 1, the first power of 7, and nothing higher. And that is why that L that you see, which is the rest of the product, is something that does not have 7, or technically speaking is a positive integer that is relatively prime to 7. So GCD with 7 is 1, where L is a positive integer such that the GCD of 7 and L is equal to 1. But when we realize n as a product of two co-prime integers or two relatively prime integers, then we know how to calculate the phi value of n. In that case, the phi value of n will be the phi value of 7 times the phi value of L, because they are relatively prime. And in fact, that's what it means when we say that the function phi is multiplicative. It just does not simply mean that when n is say AB, then phi of n is phi of A, phi of B. It's not that simple. This extra condition is needed, that the GCD of A and B should be equal to 1. Then this thing will happen. And when that happens, we say that a function is multiplicative in number theory. And phi is one such function, Euler phi function. Okay, so that means now our job is reduced in this sense. Hence, phi of n equal to, okay, we can at once use the condition that phi of n is being taken to be 24. This is equal to phi of 7 times phi of L. That is, phi of 7 is 6 times phi of L, which implies phi of L should be equal to 4. Now, if we can find those positive integers L for which phi of L is 4, then we already have got some options for n. Now, this is a very small, it's a much easier situation than actually finding out phi of n equal to 24, those n's for which the phi value is 24. It's easier to, of course, find those L for which the phi value is 4, and that you see here also you have to apply some such arguments, but here because 4 is much smaller than 24, the job is also smaller. You have to do a lot less, and this part I leave to you. Instead, what I am now going to do, I will directly write those possibilities for L. One can, so that's how I am going to continue. One can find out that the L's for which phi of L is equal to 4 are these. L equal to, I have those values here with me, and they are 5, 8, 10 and 12. You can of course simply find the phi values of these 4 integers and find that each one of them is 4, but that is, of course, is not enough. you have to also somehow argue that these are the only values of L for which the phi values are all equal to 4. That part I am leaving to you. So now that we have found these possibilities for L, we can then find the corresponding possibilities for N. Accordingly, N is equal to 35, 56, 70 and 84. So we have found 4 values of N for which the Euler phi function value, all of them are going to be equal to 24. But this is just, do you remember where we started this calculation? Here. If pi is 7, this is one possibility. Now we have to look at what happens when pi is 13. But I think before that I need to refill. But now that we have seen what we can do when pi is 7, the 13 calculation will be similar. I will do it for you, don't worry, but it will be similar. Okay. And even then, after completing the calculation for pi equal to 13, we won't be done, because this is only one part of the argument. There is another possibility. We are going back to that. Let us first see the case pi equal to 13. It's very difficult to say what one has to do, what is the precise way of approaching such a solution. That of course no one knows. We just have to look at things and look for ways to proceed so that we get something fruitful. It may not come at once. If you just simply sit down and think of a solution, you may end up taking many wrong paths before you stumble upon some path that actually works. It takes time, and experience helps. Okay. Next, if pi is equal to 13, then like we can write like this, then like above or as above. This does not sound right. Then as above we have again ki equal to 1. So that means if one argues just like the case pi equal to 7, one will get this now. 13 should divide 24. Just like there we got the wrong conclusion that 7 divides 24. So here arguing similarly will lead us to this, which is wrong. So that means here also ki cannot be greater than or equal to 2. It has to be equal to 1. So now we don't even have to write all those details. As above we have this, and hence n is equal to 13. S, L we already used, so let's just use S, where S is a positive integer satisfying hence again 24 is equal to phi of n, which is phi of 13 times phi of s, which gives us phi of s equal to 2. In this case it's even easier. Previously we had phi of l equal to 4. In this case it's even shorter, smaller. Phi of s is equal to 2, and here there are 3 options. So the options are these. S is either 3 or 4 or 6, and accordingly what should then n be? N is 13 times these things. $78. Is it really the yes? Okay. So we have got further 3 more possibilities for n, but we are not done. Now let us look at what else is there that can happen. Remember how we obtained these cases 7, 13 and 19, of course, which turned out to be a non-possibility. We got these values for pi based on the assumption that 3 divides pi minus 1, that 3 is present in that part of the product, but 3 can also be present in the former part of the product which appears first. That is, 3 may appear in the prime powers themselves, that is p1 to the power k1 minus 1, p2 to the power k2 minus 1, and so on. In that part also 3 may appear. So from that we will get some other possibilities. So that's why we next write on the other hand, I have this thing. Let me keep these values because we have found them. On the other hand, B may have pi to the power ki minus 1. Okay, should I at once write this is equal to 3 or no? Let us go logically, because we obtain these cases by considering the fact that 3 divides some pi minus 1. Now we are going to consider the case where 3 divides some power of pi, the power of pi that is available. So So first the division comes and then equality comes. In that, for some I line between 1 and n, that I am not again writing. Ideally you should write. In that case, 3 divides pi, because 3, you see here, this is the product of some numbers, pi times pi, ki minus 1 copies of pi are being multiplied together. So 3 being a prime should divide at least one of them, but they are all the same, they are all of them are equal to pi, so 3 should divide pi, but pi itself is also a prime, and that is why pi should be equal to 3. You do not just simply assume something because you feel that it is true. Each thing that you write should follow from something that is already established. So pi should be equal to 3. But now what about ki? To decide ki, okay, in this case what will happen to ki? If note one thing in the beginning itself, ki, although we just considered ki to be a positive integer, but because we have this condition, ki cannot be equal to 1. If ki is 1, then this power is equal to 1 and 3 does not divide 1. So ki must be greater than or equal to 2. So let us get rid of that case like this. Since 3 does not divide pi to the power 1 minus 1, we must have ki greater than 1 or the same thing, greater than or equal to 2. But ki may have a higher value than 2. That also we have to get rid of. If ki is greater than or equal to 3, then again we take the help of the phi value of pi to the power ki. This is equal to pi to the power ki minus 1 times pi minus 1, which actually is just simply this, because pi is 3 times 2, and this should be, of course, just like the other calculations that we came across in this solution, this should divide 24. However, now we should continue from here. So shall we lose these things? I think I need only this much space to complete everything. It may seem like this solution is very long. If it is long, then so be it. What can we do? We have to find all the possible values of n. But you may, after looking at the solution, once we finish writing everything, you may be able to shorten it. That possibility is always there. If you can, without losing any detail and without losing logic and rigor, then you should actually do it. Whatever solution of whatever exercise or problem that you ever come across, if there is a way of shortening the solution, not by making it more unnecessarily complicated, but actually simplifying it and making it easier to understand, then you actually have to do it. No matter how beautiful the original solution is, if there is a simplification possible, it should be done. However, since ki is greater than or equal to 3, ki minus 1 is greater than or equal to 2. That is, ki minus 1 is greater than or equal to 2 means what? We will have 9 here. It may be a higher power, but at least 9 will be here. 9 divides 25. So we are just simply writing the final conclusion. And this is impossible. Hence, ki must be equal to 2. It cannot be greater than 2. That is, it cannot be greater than or equal to 3. Thus, okay, now what happens to n if we now look at this prime power, pi to the power ki. This particular prime power now is 9, because 3 square, pi is 3 and ki is 2, times something. Let that something be t, where t is a positive integer satisfying this. That means 3 does not divide t. That is equivalent to this condition. Thus, 24 is equal to phi of n, that is equal to now phi of 9 times phi of t, and phi of 9 is I think it is 9 is 6, no? Because these are the positive integers less than 9 and relatively prime to 9. 4, 5, 6 is not an option, 7, 8, 1, 2, 3, 4, 5, 6, 6 integers. So phi of 9 is 6, times phi of t, or phi of t should be equal to 4. So just like before, again phi of t equal to 4. So the possibilities for t are what? What were those things? 5, 8, 10 and 12. 8, 10 and 12. I just so again we have to continue from this side. Accordingly, what will n now be? Now we have to multiply these integers by 9. So now we have all the values. And how do we know that we have actually taken into account all the possibilities? That is because you see, again, let's just see why we are actually done with this task of finding all the possible n's. This is equal to phi of n, which is 24, which is 8 times 3. From this equation everything started. Now 3 divides the right hand side, so 3 should divide the left hand side. First we considered the case that 3 divides this part, that is 3 divides at least one pi minus 1. Then we found some values of n by arguing, doing some things, and then here from this point onwards we worked with the assumption that 3 divides this part, 3 divides something here. Okay, and then we worked some more and found this some other values of n, and that's just it. This is all that can possibly happen, and that's why we are done. And we did not have to use this 8, which is see, that's why I was saying maybe if you use this 8 and argue differently, you may end up getting a shorter solution. That such possibilities are always there. This is just one solution, this is not the solution, it's a solution. So that thing is always there. Now let us conclude finally by writing all the values of n together. Hence all the positive integers n for which are n equal to, I have the values written here in increasing order. So let me just simply copy from this paper, and then you can verify that we have in fact written all the things. 45, 52, 56, then 70, 72, 78, 84, 90 and 108. Let us now just see. First we have 35, okay, then we have 39 here, then we have 45 that we have here, then 52, 52, 56, 56, 70, 72, 78 here, 84, yeah, 84 we have here, 90 and 108. So that means whatever we have here, we have here also, and we did not leave anything out. We have considered all the things. So these are precisely the values of n for which phi of n equal to 24, and here the solution ends. this question of what should an ideal solution to a problem look like, it does not have a single answer. Usually in research papers where brevity is expected, things are expected to be brief, authors will use some very slick techniques to compress the solution or prove whatever they are trying to write. So that's why when you see something in a mathematical research paper, it usually feels very difficult. But when you start to think of it, and when you start to decipher the things by putting more details into the actual solution or proof, whatever it is that you are looking at, then slowly you see that it's not that difficult. So that's why things that you see in a research paper may at once, if you just simply see the things, it may go over your head. But if you really sit down to think about it, slowly it will make more and more sense. And then you may end up seeing that it's not that difficult. But you have to appreciate the fact that the mathematicians are not doing it on purpose just to be obscure. No, they have the very difficult task of compressing things and making it as slick and as short as possible. Let us now see the next one. Let G be a non-abelian group. Let H and K, if H and K are cyclic subgroups of G. Does it follow that their intersection is also a cyclic subgroup? Prove that it does, or provide a counterexample. It does actually, and this follows from a general fact, which is that any subgroup of a cyclic group is cyclic, because you see Lee has purposefully chosen a non-abelian group G in which he is considering two cyclic groups, subgroups H and K. The nature of G as a non-abelian group actually does not play any role here. It's just there to confuse you. Once you leave the non-abelian world and come inside H and K, you are in abelian groups. That is because the intersection that we are seeing here, H intersection K, is actually it's a subgroup of G, but in particular it is actually sitting inside both H and K, so it is a subgroup of, say, H. So that means H intersection K is a subgroup of the cyclic group H, and being a subgroup of a cyclic group, H intersection K itself is cyclic. So in this solution we have to prove that fact itself. that every subgroup of a cyclic group is cyclic. That general result, although we don't need it here, so what we are going to do is that we are just simply going to consider H intersection K as a subgroup of H and prove that it is cyclic. So let's just see. Note that this is a subgroup of H, and that's just enough for us. We don't have to in fact consider K also. It is there, but let's just leave it. Now because H is a cyclic group, it is generated by some element. So let it be generated by small a, where a is some element in G. In the beginning itself, we dispose of one trivial case. If H intersection K turns out to be the trivial group consisting of only the identity element in G, then of course it is cyclic, because in that case it is also the cyclic subgroup generated by the identity element. So we now assume that H intersection K is non-trivial. Being a non-trivial subgroup of H, that means it has some element different from the non-identity, different from the identity, and any element in H, because H intersection K is sitting inside H, is some integral power of A. Thus, there exists an integer I not equal to 0 such that this. Okay, so the non-trivial element that H intersection K has, that we are choosing here, looks like this. We of course have taken I to be a non-zero integer in order to make this not equal to the identity element. But then a to the power minus I, which is the inverse of a to the power I by the rules of exponent, also belongs to H intersection K, because it's a subgroup. So this is an element, its inverse will also belong to the subgroup. So you see that I being non-zero is itself either a positive integer or a negative integer. If I is a positive integer, then a to the power I belongs to this. If I is a negative integer, then this belongs to this. Of course, in these two cases, the other elements also belong to, in fact, in both the cases, both these elements belong to H intersection K, but we are considering one at a time. The point we want to make here is that no matter what I is, whether it is positive or negative, there is always a power of A that is in H intersection K, where the exponent is a positive integer. So that's what now we are going to write. Thus, a to the power j belongs to h intersection k for some positive integer j. And this positivity will allow us to use the well ordering principle. That principle which says that any non-empty subset of the set of positive integers has a smallest element. We are now encountering, okay, let me just first write this thing completely. Positive integer j. Now this last sentence here that I have written, this gives us a non-empty subset of the set of positive integers. Do you see what that subset is? It is the set of those positive integers for which this thing is true. This is of course a subset of the set of positive integers, which are we denoting that by n in this book? I forgot. Okay, if you just for the sake of definiteness and to get rid of confusion, let me just write it like this. This is a subset of the set of positive integers. It is non-empty because j belongs to this. So by the well ordering principle, this set will have a smallest element. In other words, putting things more simply, there exists a smallest value of j for which a to the power j belongs to this. And now we are going to write that. Every now and then we keep on using the well ordering principle, and we use it so much that we don't even bother writing something like that. We are using the well ordering principle, it's understood. Hence, so keeping up with that practice, we don't write anything further. We don't even mention the well ordering principle. Hence, we just directly write like this. There exists a smallest positive integer, let it be denoted by j naught, such that this belongs to H intersection K. Now our claim is that this actually is the element, is one generator of H intersection K, which will prove that this intersection is the cyclic subgroup. We claim to prove this claim, what do we have to do? You take any element here, you have to prove that that element is an integral power of this power, a to the power j naught. Let a to the power j, so this is any arbitrary element here in this intersection. Why does it look like that, a to the power j? Because ultimately this thing is inside H. No? So whatever element you take, that should be an integral power of A, where A is a generator of H. So let this belong to H intersection K, where of course J is some integer. Now positive or negative, we don't have to consider that. By the division algorithm, or some people call it the Euclidean algorithm also, we can divide this integer j by j naught to get a quotient and a remainder. So by that result, there exist integers q and r such that j is equal to q j naught plus r, where the remainder r is non-negative and strictly less than j naught. So then what shall we get from this new information? That we can write that a to the power j now in terms of this thing, this expression for j. So this is equal to a to the power q j naught. Did I write not everywhere? Yeah, okay. Plus r, which by the rules of exponent equals this product. Hence, and from that we get this minus q. Okay, now you see a to the power j naught is in h intersection k, so its integral power, where the exponent is any integer, will also belong to h intersection k. In particular, this one, this minus qth power of a to the power j naught, will belong to h intersection k, and according to our choice, this a to the power j also belongs to h intersection k. Because this thing is a subgroup, this product will belong to h intersection k. That means a to the power r belongs to h intersection k. Now concentrate on these inequalities. R is a non-negative integer strictly less than j naught. Can r be positive? R actually cannot be positive. What goes wrong if r is positive? If r is positive, then you are getting a positive integral power of a which belongs to h intersection k, where the exponent r is less than j naught. But this contradicts the minimal nature of j naught. See, there exists a smallest positive integer j naught for which this thing will happen. So no smaller positive power of a, for such a thing should the same thing happen, for no such smaller integer. That is why, because r is already smaller than j naught, it cannot be positive. It has to be equal to 0. And we are going to write all these things in just one line like this. By the minimal nature of j naught, we must have r equal to 0. And what is the consequence of that? That is, j then must be equal to q j naught, or a consequence of that in turn is this: q j naught, which by one of the rules of exponents equals this. That means an arbitrary element of H intersection k has been realized as an integral power of a to the power j naught. So what does that tell us? It tells us precisely this, that H intersection k is a cyclic group that is being generated by this element a to the power j naught. Thus, and this establishes our claim and completes the solution also. Since the two solutions that we went through in this video so far have been somewhat long, so let's just stop things here itself. We will continue from the other exercises in the next videos. And with that, I end this video, of course. If you want to say something about these things, positive, negative, anything, you please write in the comment section below, or you can mail me at my address. The link as usual will be there in the description. And tomorrow we are again going to study infinite series of real numbers. So that being said, I wrap things up for tonight. So see you tomorrow with real analysis, specifically where we are going through infinite series of non-negative real numbers actually. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.